Hello again, welcome to another lesson in Algebra 1. Today we're covering model inverse variation, which is section 12.1 in your book. Okay, read the following to help remind you about direct variation. Recall two variables x and y show direct variation if y equals ax and a is not 0. So in other words, the variables form a linear equation, which means the graphs to make a line with the y-intercept of 0 and the slope not being 0. This is a direct variation because one variable increases in magnitude. The other variable also increases in magnitude. For example, the weight of an object made from steel will increase as its size gets bigger. Okay, so this is the size of the object, how much steel it is, and this is its weight. And if its size is 0 amounts of steel, its weight is 0. And as the size increases, the weight also increases. All right. All right, number 2, rewrite 2x minus 5y equals 0 as a direct variation equation. That means I need to make it in this form. So that just means solve for y. So negative 5y equals negative 2x. Divide both sides by negative 5, and we get 2/5 x. Now remember, this 2/5 is usually called our slope, but in a direct variation equation, it gets a special name. This is our constant of variation. It's the number that tells us how to relate the x and y variables together. Okay. All right, number 3. The number of words you type on a keyboard varies directly with the number of minutes m that you type for. You can type 360 words in 8 minutes. Complete the following direct variation equation to show the number of words as a function of its minutes. So the number of words is supposed to be a function of the minutes. And if we work out this, we'd find out that's 45 simplified. So 45 should go on this line. All right. Now you should always check yourself with the input-output pair that we have here. So 8 is supposed to make 360. And if we plug 8 in for m, 45 times 8 does make 360. So this is the right equation. Okay. So our constant of variation in this problem, one more time, is 45. Okay. Use your direct variation function to determine how many words you can type in 12 minutes. So that's just saying plug in 12 for the number of minutes and see what it works out to. And if you type that on your calculator, it should make 540. Okay. So you can type 540 words in 12 minutes. All right, our last one, number 4, says graph the direct variation equation y equals 2/3 x on the grid. So remember, direct variation equation always going to have a y-intercept of 0, but you can see there's nothing being added on the end, no constant term here. So we go up 2 and over 3, up 2 and over 3, up 2 and over 3, and up 2 and over 3. And here's our line. Okay, so y equals 2/3 x. All right, let's flip it over and see about inverse variation. Inverse variation. The variables x and y show inverse variation if y equals a over x. So last time, direct variation is y equals a times x. This is a divided by x. And once again, a cannot be 0 or we don't have any kind of variation at all. So the non-zero number a is still called the constant of variation. And y is said to vary inversely with x. Okay. Here's a practical example. Create a graph to show all the possible length width pairs that can be used to create a rectangle with an area of 20 inches squared. So if the width was 10, the length would be 2, and that area would be 20. If the width was 5 and we wanted an area of 20, then the length would have to be 4. If the width was 4 and we wanted an area of 20, the length would have to be 5, and the width was 2, and we wanted an area of 20, then it would have to be 10 here, so 2 times 10 for 20. There are also many other pairs, but we're going to graph these to see what our graph would look like. So the first one would be 10, 2. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and up 2. Okay, so 10 to the right and 2 over. And then 5 to the right, 1, 2, 3, 4, 5, and 4 up. Okay, and then 4 to the right and 5 up, and 2 to the right and 10 up. 6, 7, 8, 9, 10. All right, so you can see this graph does not make a line, okay? And there's going to be other things that would make this true, like for instance, we could go up 1 and over 20, or 1 over and up 20. Either way we wanted to do it. And then lots of fractional values in there. But when we're done, we're going to get a weird curve here, okay? Now this curve is never going to cross over the axis, because there's no way I could pick 0 for the width and get a length that would make it multiply to 20. And it's never going to cross over this axis, because there's no way I can pick the length of 0 and get a width of 20. So what we do is we draw 2 dotted lines on there. Those dotted lines have a special name we'll talk about in a minute. And the green graph would never cross over those 2 dotted lines. So our graph here is y equals 20 over x. Okay? Or in our case, our input variable was width and our output variable was length. So length equals 20 over width. Okay? So what is the equation? That we just wrote it. Our length is equal to the 20 divided by the width. We can double check ourselves by just picking a variable that we did up here. So we can say, okay, well, if the width was 10, that means 10 would go here. 20 divided by 10 would make 2, which is what it's supposed to. So if I put a 10 in the width, I'm going to get a 2 for the length. Okay. What is the constant of variation? Well, the constant of variation is 20, and notice it's what each time it always multiplies to. Okay. All right. Why does the graph need dotted lines on the x and y axis? And one more time, this is because the width and length can never be 0. So our graph can't cross. The axis. Okay? So if the width and length can't be 0, then the green graph up here can't cross over those 2 red dotted lines. All right? So in your homework tonight, you're going to have questions like this. Tell whether each question represents direct variation, inverse variation, or neither. So in other words, it's saying, does it fit this model, y equals ax? Does it fit this model, y equals a divided by x? Or does it fit neither one? If you look at number 1, this is definitely fits the model y equals a over x. So this is inverse variation. If you look at number 2, we'd have to solve for y first to see what's going on. So we'd have 3/4 x. This fits the y equals ax. So this is direct variation. If we look at number 3, we first solve for y. So we have negative y equals negative 5x plus 3. So y is equal to 5x minus 3. And this is neither one. It does graph as a line, but the y-intercept is not 0. So it doesn't fit the y equals ax form. All right, and number 4, I'm going to first rewrite this as 0.5 to help us understand what's going on. I'll divide both sides by x, so this is 0.5 over x. And that fits our y equals a divided by x form, so this is inverse variation. Okay. All right, so the graphs of inverse variation have a special name. They're called hyperbolas. Okay. So the graph of inverse variation is a hyperbola. The lines where the branches of the hyperbola do not intersect are called the asymptotes. So our branches are the graph, which up here would be the green thing, and the dotted lines are the asymptotes. Now there was a whole nother branch to our graph that we did not draw in this first problem up here, and that's because it didn't make sense to multiply 2 negative lengths together, because you can't have a negative length. But mathematically, it would make sense because 2 negative numbers can multiply to positive 20. All right. So let's flip it over and draw some branches for graphs and the asymptotes to go with it. All right. On number 5, we have y equals 4 over x. So for inverse variation, the x and y pair should always multiply to the constant of variation. So here we're just trying to think of numbers that can multiply to 4. So for instance, 1 and 4 would work. So we could plot a point at 1, 4. 2 and 2 would work. So we could plot a point at 2, 2. 4 and 1 would work. We could plot a point at 4, 1. That's all the whole number ones that will fit on our graph, but we need some other points. So we could plot 8 and 0.5. Half of 8 is 4, so that works out fine. And we could also plot 0.5 and 8. So 0.5 over and 8 up. And this will give us enough to draw our graph on this side. Now that red line is going to keep getting closer and closer to the x and y axis here. But it's never going to touch it, because if I let one of the variables be 0, there's no x, oops, that's supposed to be dotted, or y that could multiply with 0 to make it turn into 4. Okay, so we put these asymptotes here, and we put an asymptote here. And that represents the fact that nothing could pair with 0 to make it multiply to 4, and nothing could pair this way with 0 to make it pair go by 4. All right. Now there's a whole nother section to our graph, a whole nother branch. And those are these answers: -1 and -4, -2 and -2, -4 and -1, etc. So the opposites of those, so -2, -2, -4, -1, -1, -4, and then the 1/2 one out here. So we have our other branch of our graph on this side. Okay, so a hyperbola has two branches, the red parts in this graph, and then dotted lines called asymptotes that split those branches apart. Our red branches will never cross over an asymptote. All right, and our next one, plot all of our points here. So we're looking for things that can multiply to -10. So -1 and 10. So let's draw it in red again, just like we did last time. So -1, -10, that's, or +10, that's up here. And then we could have -2 and +5. That's 2 over and 1, 2, 3, 4, 5 up. Okay. Or +5 and -2. That's 5 over and 2 up. Or +10 and -1. That's 10 over and 1 up. So we can see how our graph branch is going to be up here this time in the second quadrant. And the reverse of this would be, oh, I'm sorry, this was supposed to be negatives and positives. The reverse of this would have been 1 with -10, 2 with -5, or 5 with -2, and 10 with -1. So that's going to be over here, 10, -1, 5, -2, 2, -5, and 1, -10. So here's our other branch. Okay. And then we still need to draw our asymptotes, because these graphs are never going to be able to cross our axis, because there's nothing I could pair with 0, and either way, whether I made x or y be 0. All right. So what happens is, if we have a positive constant of variation, we get our graph, our branches in quadrant 1 and quadrant 3. If we have a negative constant variation, we get our graph, our branches of our graph in quadrant 2 and quadrant 4. All right. Number 7, the variables x and y vary inversely. And when y is -2, x is equal to 12. Write an inverse variation equation that represents x and y. And then we're going to do a second part. So I know that my constant of variation should be the xy pair multiplied together. So in this case, it's going to be -24. So I can say y equals -24 over x. There's my equation. Okay. Second part, find the value of y when x is equal to -3. So y equals -24 over -3, and this will make 8. There's my second answer. Now on our first answer, we should always check our ordered pair that we know. So the ordered pair was 12, -2. If I plug 12 in for x, that would go right here. Okay. Then -24 divided by 12 would make -2, which would go in this spot. So it does work. All right. Number 8, tell whether the ordered pairs -5, 2, -4, 2.5, 8, -1.25, 20, -5 are a direct variation. Okay, do they represent inverse variation actually? Okay, so Way we do this is we just multiply each pair. So the first pair multiplies the negative 10. The second pair multiplies the negative 10. The third one multiplies the negative 10, and so does the fourth one. If all the ordered pairs multiply to the same number, they're just like above here, then we know that we have inverse variation. So our first answer is yes. If so, write the inverse variation equation, and our second answer would be, well, that negative 10 is our constant of variation, so y equals negative 10 over x. All right. So remember, for inverse variation problem, the x and y should always times to the same thing over and over again. If we look back up here, all of these pairs of x and y, except for the 0 ones on the bottom, multiply to negative 10. All of these pairs multiply to 4. That's what makes it inverse variation. All right. And in our last question, suppose a mining company estimates that 20 people working 270 hours each could complete a job. Find the work time per person if the company hires 30 people. So we want to know how much work time there are, so how many hours based on the number of people. And we need to know that constant of variation. Okay, so 20 people, that's our input, makes 270, that's our output, 270 hours per person. So our constant of variation is going to be 20 times 270, because an input and output multiplied together will always be the constant of variation for an inverse variation problem. So this is going to be 5,400. So here's our equation. The number of hours the person has to work is 5,400 divided by the number of people. Okay, so basically it takes 5,400 total hours to complete the job. Now we're saying, what if we hired 30 people instead of 20? How fast would the job go? So each person would have to work, let's see, 5,400 divided by 30, which was 180 hours. All right, so what's the work time per person? 180 hours. All right, so your homework was page 769, problems 3 through 57, multiples of 3. All right, I will see you in class next time. We'll go over the homework, take a quiz, and then learn some new stuff.